Recycled tire rubber, hybrid GTR binders, and dry-added GTR, how to use them in asphalt pavement mixtures. The Federal Highway Administration has an ongoing accelerated implementation and deployment of pavement technologies program, which includes deployment of innovative technologies to improve pavement performance and reduce agency risk. This presentation was prepared by Galen Baumgartner in July 2022 under the Development and Deployment of Innovative Asphalt Pavement Technologies Cooperative Agreement with the University of Nevada, Reno. Presenting today is Galen Baumgartner of Paragon Technical Services, Inc., Jackson, Mississippi. This material is disseminated under the sponsorship of the U.S. Department of Transportation in the interest of information exchange under Cooperative Agreement number listed. The U.S. government assumes no liability for the use of this information. The U.S. government does not endorse products or manufacturers. Trademarks or manufacturers' names appear in this material only because they are considered essential to the objective of the material. They're included for informational purposes only and are not intended to reflect a preference, approval, or endorsement of any product or entity. This presentation is arranged into 7 sections corresponding to selected major headings of the companion publication, Recycled Tire Rubber, Hybrid GTR Binders, and Dry-Added GTR, How to Use Them in Asphalt Pavements. First, a brief introduction will be presented, followed by a section of background information. Section 3, Mixture Types, discusses 3 common mixture types. Section 4, Binder Stabilizing Agents, are briefly discussed to note their function and importance. In Section 5, Mixture Design considerations are given. In Section 6, a discussion of mixture performance tests is provided. And in Section 7, Summary provides summary comments and discussion. First, a brief introduction. The Recycle Material Policy regarding sustainable infrastructure was established by the Federal Highway Administration in 2006. The policy states that recycling and reuse can offer triune benefits of engineering, economic, and environmental impact. Pavements with longer service lives should involve less maintenance and are environmentally friendly from the perspective that they involve less greenhouse gas, generating less attention per unit use. Pavements with longer service lives are more economical and more efficiently serve public needs, which increases social well-being. The primary objective of this presentation is to provide knowledge for resource-responsible use of ground tire rubber, GTR, in asphalt pavement mixtures. Technical information is given on the background of recycled tire rubber use in asphalt pavements and information related to design and performance of GTR modified asphalt mixtures, as well as considerations for GTR modified asphalt mixture design. This project is sponsored by the Federal Highway Administration Project Deployment and Development of Innovative Asphalt Technologies, specifically related to resource-responsible use of materials in flexible pavements. An accompanying technical report entitled Recycled Tire Rubber, Hybrid GTR Binders, and Dry-Added GTR, How to Use Them in Asphalt Pavement Mixtures, is available at the FHWA website. The links to this website are given on this slide. Additionally, there's a link to another previous GTR publication that is also of benefit if one is interested. In 2019, scrap tire markets consumed 75.6% of the estimated 4.5 million tons of scrap tires, 272 million scrap tires generated annually. The 3 largest scrap tire markets reported by the U.S. Tire Manufacturers Association were tire-derived fuel, which accounts for 36.8%, consisting of cement kiln, pulp and paper, and industrial boiler applications. This was a 5.2% decrease from what the UTMA reported in 2017. GTR, ground tire rubber, accounted for 24.4% of the total consumption with use in asphalt, automotive molded and extruded products, playgrounds and mulch, and sports surfacing applications. This was an increase of 7.5% over reported consumption in 2017. Civil engineering consumption was 5.1%, including tire shreds used in road and landfill construction, septic tank leach fields, and other construction applications. Civil engineering consumption dropped by 28.4% 4.5% over 2017 reported consumption. Recycling of waste tire rubber from tires into GTR involves grinding or reduction of tire rubber into smaller particle size, which results in an increase in surface area. The rubber grinding industry classifies GTR according to particle size as rubber which is 2.0 millimeters tin mesh and smaller. The typical size of GTR used in modified asphalt binders and mixtures for pavement construction range from about 1.5 millimeters or 1,500 microns down to about 0.42 millimeters, 420 microns, 14 mesh to 40 mesh, with limited use sizes as small as 177 microns or 80 mesh, and even 125 microns or 120 mesh. The GTR market is reported to at slightly more than 1 million tons or about 66 million scrap tires. GTR modified asphalt pavement represents 17% or approximately 180,000 tons or 11.3 million scrap tires. Asphalt modification showed an increased consumption of 4.1 million scrap tires from 2017 to 2019, or an increase in consumption of 51.3% over 2017 reported consumption. There are currently two primary processes for incorporating GTR into asphalt binder and mixtures, referred to as either the wet or the dry process. Wet process blends GTR and asphalt with one of two technologies, asphalt rubber (AR) and rubber modified asphalt binder (RMB). RMB technology may be referred to as terminal blend. AR is generally produced on site at an asphalt mixture plant with a prescribed reaction time prior to mixing the GTR modified binder with aggregates. Conventional RMB consists of GTR modified binder containing only GTR as the modifier. Another common terminal blend technology referred to as hybrid GTR utilizes GTR and other modifiers such as styrene butadiene styrene (SBS) block copolymers. Dry process technologies incorporate GTR directly into the asphalt mixture during mixture production. Dry added rubber is usually added directly to the aggregate in the asphalt plant mixing drum prior to introduction to the asphalt binder. Background information. Research on GTR modified asphalt binders over the last 50 years has shown favorable impacts of GTR modification. GTR ranks second among the most common asphalt pavement modifiers behind styrene butadiene styrene block copolymers. Modern GTR use in paving began in the early 1960s with a highly elastic asphalt rubber. The work expanded into larger chip seal projects along with other crack relief interlayers and open graded friction courses. During the two decades following, AR materials increased as they proved useful in various pavements, maintenance functions, applications, including asphalt pavements. But by far, the greatest utilization during the time frame was maintenance applications. During this same time frame, versions of dry mixture addition of GTR to asphalt mixtures posed more of an issue than dry processes employed today. The primary difference between the dry process technology of the 1960s and 70s compared to today's dry process technologies relates to GTR particle size and GTR dosage. Additionally, co-additives that aid in mixing and compaction, mixing and placement and compaction have been employed. These additives have included processing aids from the tire manufacturing industries, such as I'm sure you've heard of Vestinomer, or Fischer-Tropsch waxes and Steramid waxes. GTR modified binders have been successfully used on three general asphalt mixture types: dense graded, gap graded, and open graded. Traditional mix design procedures have been used to design mixtures with both wet and dry processed rubber. Mixture design volumetrics are important in design of mixtures containing GTR modified asphalt binder or dry added rubber. However, volumetric mixture design procedures may not provide mixture performance desired. It is important to consider the rubber component of the binder and how it may affect volumetrics. The balanced mix design approach may be more suited for design of GTR modified systems. Regardless of design method or application, the design of asphalt mixture is a balancing act combining selection of aggregates and asphalt binder proportion to provide desired performance. Asphalt mixtures are designed to provide workability necessary to construct an in-place pavement resistant to permanent deformation, fatigue, low temperature cracking, and moisture damage, as well as provide a skid-resistant, smooth-riding, durable surface. Of primary importance is achieving the overall performance goal or effective asphalt mixture design is asphalt binder content. Excess asphalt binder content may lead to stability issues or mixture susceptible to pavement deformation, whilst insufficient asphalt binder content may be the cause of durability issues such as premature pavement cracking. Most state DOTs use the SuperPave method as specified in AASHTO R35 standard practice for SuperPave volumetric design for asphalt mixtures and AASHTO M323 standard specification for SuperPave volumetric mix design to identify the optimal aggregate blend and optimum asphalt binder content. Some state DOTs still rely on earlier methods such as the Marshall and Bean methods of mixture design or employ local modifications or adjustments to AASHTO standards. Use of AASHTO standards is not a federal requirement. The public concern typically is not about design of asphalt mixtures, but about smooth, comfortable ride and desirable performance over an extended pavement life. A brief discussion of mixture types. GTR modified binders have been successfully used on the three general asphalt mixture types: dense graded, gap graded, and open graded. Mixture design volumetrics are important in design of mixtures containing GTR modified asphalt binder or dry added rubber. However, volumetric mix design procedures may not provide mixture performance desired. It is important to consider the rubber component of the binder and how it may affect volumetrics. The balanced mix design approach may be more suited for design of GTR modified systems. Now let's discuss wet process dense graded asphalt mixtures. Marshall, Veeam, and SuperPave have been used to design dense graded mixtures with GTR modified binders. In dense graded mixtures, GTR modified binders generally increase optimum binder content and lower laboratory stability compared to conventional asphalt dense graded mixtures. This is generally a result of the asphalt rubber binder, or in some cases rubber modified binder, having higher viscosity relative to conventional asphalt binder, preventing close packing of the aggregate, thereby needing more binder to get the same level of voids in total mixture, or VTM. Use of asphalt rubber binders with higher GTR concentrations, 15 to 20%, for example, is not common in DGA but may occur. GTR in dense graded asphalt mixtures is typically in the form of asphalt rubber binders with a reduced GTR contents less than 10% or rubber modified binder technology of the same GTR concentration. Wet process GTR binders used in gap graded mixtures also have used Marshall, Veeam, and SuperPave mixture design to design gap graded mixtures. Gap graded mixtures are generally used with asphalt rubber technology in place of dense graded asphalt mixtures. GTR concentrations may be in the 15 to 22% range. Gap grading generally consists of removing a portion of the fine aggregate to allow room for rubber particles within the gradation. Typical binder contents of gap graded mixtures are in the 6 to 8% range. Open graded asphalt mixtures are more common with wet process GTR modified asphalt binder, particularly with the asphalt rubber technology. A common test for open graded friction cores in stone matrix asphalt is binder drain down to ensure that binder does not flow off the aggregate during normal production, placement, and compaction. Stabilizing agents are often used to aid in resistance to asphalt binder drain down. Sometimes warm mix additives may be used with GTR modified systems, allowing lower temperatures, which aids in prevention of drain down. It is important to consider the contribution binder stabilizing agents offer to mixture durability before foregoing the use of stabilizing agents. Dry process GTR modified mixtures have been designed using standard mix design methods as well. Criteria for selection of optimal binder content may be different than typically used in these methods. Laboratory designed mixtures are prepared by pre-blending heated aggregate and rubber followed by addition of the asphalt binder. Laboratory stability and stiffness values of dry process laboratory asphalt mixtures have been reported to be lower than values of conventional mixtures. Now a brief comment on binder stabilizing agents. Binder stabilizing agents are most often fibers such as cellulose, mineral fibers, polypropylene fibers, or polyester. The stabilizing agents have potential of reinforcing and improving cohesion of the tensile strength of the mixture. They permit higher asphalt binder content without significant drain down issues, provide thicker films, and enhance durability. Typically used in mixture addition levels of about 0.1 to 0.4%, depending on stabilizing agent and mixture type. Sometimes the additives are considered to be difficult to deal with, to handle, but they do provide additional benefits to the mixture other than just drain down prevention. So it's very important to consider these added benefits before foregoing the use of binder stabilizing agents. Mixture design considerations. Let's discuss a few important points to consider with respect to GTR when it comes to mixture design considerations. First, GTR is a thermoset polymer. GTR does not melt in asphalt or asphalt mixture. GTR modified asphalt binders are dispersions where the GTR particles are dispersed in the asphalt binder. GTR particles absorb lighter asphalt components, swelling the GTR particles to as much as 5 times their original size. Dispersion and solvation are primarily responsible for the increased stiffness and elastic nature imparted to the asphalt. So it's this that gives the asphalt the elastomeric nature or the rubbery nature that it gets from the GTR modifier. Blending time, temperature, relative surface area, and GTR asphalt binder compatibility affect these interactions. So that's what determines the performance of the GTR modified binder or GTR modified mixture. Several factors influence GTR particle asphalt interaction, several of which are interrelated. When GTR modified asphalt binder or GTR is introduced into asphalt mixture, these factors should be considered by the mixture designer. The most obvious of these factors is the amount or loading of GTR incorporated. Other factors are related to how much investment would be involved into incorporating the GTR into the final asphalt mixture. A question one might ask is, what is the total mixing investment related to incorporation of the GTR into the asphalt mixture? Understanding that investment is not necessarily monetary. This figure gives a general idea of how much investment might be involved in incorporating GTR into the final asphalt mixture, as illustrated on the vertical axis, total mixing investment. Again, investment in this case is not necessarily monetary. Investment relates to GTR particle size, processing conditions such as agitation and mixing level, processing temperature, and processing time. Remember, generally smaller particle size processed at higher temperatures for longer times under higher shear conditions result in greater incorporation of GTR's performance properties into the asphalt mixture. The area in the lower right portion of the figure labeled generally avoided results from possible lack of success of earlier dry processes. These processes may have used too much GTR or GTR with too large a particle size. The similar area in the upper left is obvious. Directly affect asphalt mixture performance, irrespective of the asphalt mixture design method employed. The amount of GTR in the formulation is the only factor that can be accounted for with volumetric principles during mixture design. For example, GTR has been characterized as a two-component post-consumer polymer system having functional polymer and filler. Functional polymer is the portion of the GTR, usually about 30 to 40% of the GTR, that is reclaimed polymer serving as the asphalt binder modifier. The remaining filler portion of the GTR, the remaining 60 to 70%, consists of inert matter such as carbon black, mineral filler, residual fibers, etc. This should be given consideration when designing asphalt mixtures containing GTR or GTR modified binder. A common practice with some state DOTs has become to increase the asphalt design binder content by 0.2 to 0.3% to address lean mixture concerns and early age cracking of GTR modified systems. This figure is a simplified phase diagram showing the volumetric conditions of interest relative to GTR modified asphalt mixture design. The companion technical report has a detailed discussion of this topic. The total volume is designated by V sub T. Figure A is a reference case with no GTR or other recycled materials, which is the scenario for which the volumetric mixture design was originally developed. This is figure A. An asphalt mixture's total volume, V sub T, is defined by the bulk volume occupied by the stone or equivalent inert material denoted as V sub V, volume of stone, plus the voids in mineral aggregate or VMA. The volume of stone, bulk volume of the stone, encompasses the asphalt binder absorbed into the aggregate, while VMA encompasses air volume, asphalt binder volume, and the ingredients within the asphalt binder that are deemed to be asphalt binder. So this is the bulk volume of the stone, V sub B, and this top portion is VMA. The minimum VMA is designated by the dashed line that you see here. In the case of GTR modified binders, minimum VMAs may be as high as 17%, whereas in dense graded mixtures it may be lower, like 13%. So if you see a larger minimum VMAs, that's pretty common, especially with GTR because of open graded mixes or gap graded mixes. A key to asphalt mixture design to consider is how to evaluate non-asphalt components, especially with high GTR loadings, and that's what we'll discuss with these other three diagrams. Now let's turn to figure B, GTR and binder with reduced VMA. Actually, this is not optimal. If the total volume of GTR is denoted by V sub GTR, the functional polymer previously tested can be denoted by V sub GTR dash polymer, and the filler can be denoted as V sub GTR dash inert. In this example, V sub GTR polymer is essentially equivalent to the effective binder volume, or V sub BE. Basically, GTR cannot be added to any asphalt without volume being available to accept it. There has to be room for both the GTR polymer and the GTR inert. The asphalt designer should be aware of how much volume is going to be needed per unit of GTR. GTR is an ineffective material per unit volume by comparison to typical modifiers, example SBS. Remember earlier we discussed that GTR is a two-component material with about 30 to 40% functional polymer and about 60 to 70% inert material. For the purpose of this discussion, in figure B, half of the GTR volume can be considered as functional polymer, and the remainder will be considered as inert. So we've got a 50-50 block of material there, if you will. Considering V sub GTR inert as part of the binder would be overestimating the actual VMR, yielding less VMA than desired. Remember, I mentioned this is V sub BE, but if you've got both the inert and the polymer, you're treating that all as binder, which actually overstates the actual VMA, which can yield less VMA than desired. Figure C presents the optimal consideration with half of the GTR volume V sub GTR polymer being considered as VMA and the remaining half V sub GTR inert being considered as V sub SV or as volume stone or part of the bulk volume of the stone. This is optimum because now this GTR polymer or V sub BE or the volume effective binder is in the VMA and it doesn't have with it the non-binder material or the inert material. Figure D depicts dry added GTR where none of the GTR volume is considered as part of VMA as the V sub GTR polymer is only modestly activated by the dry addition process. Considering the preceding discussion, we can use baghouse fines as a comparison. Baghouse fines do not count as part of VMA. Similarly, inert filler component of GTR should not be part of VMA. Inert components of GTR are not affected by being incorporated into the asphalt binder. Some methods consider them as part of the aggregate V sub SB when dry added to the asphalt mixture, but consider them as part of VMA when blended with the asphalt binder. And that's exactly what you see here. They're considered part of VMA when blended with asphalt binder. In this case, they're more part of stone, and even the V sub GTR polymer is considered part of the stone. And this is primarily because the design of the mix was designed prior to addition of the rubber, so we already had the VMA and V sub SB, and when you add the rubber, it basically becomes part of the stone or the bulk stone with only a minimal portion contributing to the VMA. If inert components are considered as part of VMA, effective binder may be reduced by the volume of the inert components, leading to less than optimal effective binder content. And that's easy to understand. Mixture design with performance test, better known as balanced mix design or BMD. Mixture design discussion thus far in this presentation has been mostly limited to design based on volumetric properties, combining select quality appropriate aggregates and asphalt binder properly proportioned to provide desired performance. BMD is an asphalt mix design using performance tests on appropriately conditioned specimens that address multiple modes of distress, taking into consideration mix aging, traffic, climate, and location within the pavement structure. BMD incorporates 2 or more mixture performance tests focused on stability, permanent deformation, rutting, and durability or cracking, assessing how well mixture resists these common distresses. The Association of State Highway Transportation Officials AASHTO PP 105-20 standard practice for balanced mix design in asphalt mixtures describes 4 approaches, A through D, for BMD process. This is a voluntary standard and is not a federal requirement. With GTR, applicable performance test criteria may be different than for conventional DGA mixtures. Deformation, rutting, and durability and cracking to assess mixture resistance to these common distresses. And this is the same diagram we used earlier to talk about mixture design and the balancing act, but you can see we have to select the optimum acceptable binder range to give us the maximum stability and the best stability and the best durability. Because if we have too much binder, then we could have stability issues, which could lead to rutting, permanent deformation. And if we don't have enough binder, then we could have durability issues, which could lead to early cracking or raveling or degradation of the mixture. So the optimum of balanced mix design is to determine the minimum allowable durability and the minimum allowable stability to give us, for a given traffic load, to give us the range of acceptable binder that we need to provide the performance desired to resist cracking and to resist rutting. So it's the acceptable asphalt content to resist cracking, and to resist rutting. We have selected a realistic example to look at dense graded asphalt. And in this case, very often you'll hear with GTR that to avoid dense graded mixtures and avoid dense graded mixtures on the fine side of the maximum density line. In this case, we decided to do exactly the thing that they recommend that we not do. So we chose a dense graded gradation that was pretty much on the fine side of the maximum density line. We want to see how that worked with different rubber asphalt GTR modified asphalts. DGA, or dense graded asphalt, is a common mixture type used in asphalt pavement construction. It is widely used as a base course, binder course, and a surface course. So you can see it could be used quite often, and so it's a mix that could have a lot of uses for GTR modified binders. Again, it's suggested that use of GTR modified binders avoid gradations such as the one in this diagram. While SMA and OGFC mixtures may be somewhat more favorable to GTR because of the gradations are more open, allowing for easier incorporation of GTR into the mixture matrix. However, SMA and OGFC are especially surface mixtures, which with limited use compared to DGA. As I said, DGA is used in surface, binder, and base. DGA, or dense graded mixture, could offer the greatest opportunity for increased use of GTR modified binders and reuse of old tires or discarded tires. We selected 4 binders: a neat binder, which was a 64 minus 22, graded by ASTO M320 and ASTO M332. Graded by ASTO M320, it was a 64 minus 22, and M332 was a 64S, or standard minus 22. And then modified with 5, 10, and 15% GTR, 30 mesh GTR in this case, and graded accordance with ASTO 320 and M332. So basically 5% was a 70 minus 22, or a 64H heavy minus 22. A 676, the 10% was a 76 minus 22, or 70E minus 22. And the 15% was a 76 minus 2E according to M320, and a 70E minus 22 according to M332. For the purpose of our balanced mix design consideration, we chose the Hamburg wheel tracking test to look at the performance of these mixtures, this mixture with these different binders in permanent deformation or rutting performance. So we look at rut depth, where typically the failure limit is 12.5 millimeters after 20,000 cycles. We did 5, 10,000, 15,000, 20,000 passes on the Hamburg wheel tracking device. What you see here is that these materials, you would expect the 15% GTR to perform the best. However, in every case, it performed really not much better than the original binder. In some cases, it performed better, but the point is that you would expect it to perform better than the 5%, better than the 10%, etc. And in this case, none of them passed the 12.5 millimeter limit. This is a good example of the rubber there not being room for the rubber in the mixture. And it shows you the example that we discussed earlier in the mix design considerations on those phase diagram looking at BMA. But again, we chose this mix because we knew that there wouldn't be room. We wanted to see how it performed. We adjusted the gradation after seeing the failure or the lack of performance that we expected on the Hamburg wheel tracking test. We decided to adjust the gradation. So we adjusted the gradation, remaining on the fine side of the maximum density line, but not a grap graded mix, just enough of the aggregate to make room, or the fines to make room for the rubber in the same area where we felt like the rubber or the inert materials were affecting the gradation. So it's not a gap graded mix, just removing enough of the aggregate in the area of the GTR particle size to make room for GTR and inert fraction. After adjusting the gradation, we repeated the Hamburg wheel tracking test with the same materials, and you can see now there's a difference in the performance and the way they performed. In the case of the higher loading of GTR, actually did perform either the same or better than the lower loading of GTR. This is the 5%, 15%, and I'm sorry, 5, 10, and 15%. So out here at the 20,000 passes, the 5% really performed a lot like the original binder, and the 15 and the 10 and the 15% performed equivalent. Another thing we did, we wanted to look at how other binders, rather than just those 3 binders or those 4 binders, would look with so we actually formulated some other binders with 10% GTR, 20 mesh, 30 mesh, and 80 mesh, and then we did a 7622 SBS modified, and the hybrid, which was about 1.5% of SBS plus about 7% GTR, and graded those according to M320 and M332. Basically, they were all 7622 or better. The 7622 actually graded as an 82 minus 22. If you looked at the M323, the 76 minus 22 with 20%, 10% 20 mesh rubber, graded as a 64V, very heavy, minus 22, and then 64V for the 10% and 64V for the 30 mesh, and 64V for the 80 mesh. So you can see that the different rubber particle sizes gave us the same PG grade. The 76 minus 22 actually graded as a 70E minus 22, and the hybrid GTR was also a 64, but it was a 64E minus 22. Hamburg wheel tracking tests were performed on these, except in this case we used the original dense graded gradation. So it's the original gradation, not the adjusted gradation. Indications are that these asphalt binder formulations are more adaptable to fine graded DGA with gradations such as the original unadjusted design blend gradation. This shows you the benefits of the balanced mix design approach, because we did this with the original gradation and we saw what happened when we adjusted for it with the just the 3 rubber modified binders. So you could see that we could do the same thing here, but you can see here that these materials performed, again, the rubber materials performed very similar to what we saw in the previous example, except the 80 mesh, which we thought would incorporate better, actually didn't perform as well as the 20 or the 30 mesh. And then the SBS and the hybrid, or the materials, this is the hybrid here, and the SBS, the hybrid material actually performed in all cases a little bit better than the SBS modified, even though the SBS modified graded as a higher grade. So there's some synergy there between the rubber and the SBS that we may not be capturing in some of the binder grading, but we did see in the mixture testing. This slide is mixture BBR testing of the neat 64 minus 22 and the 5, 10, and 15% 30 mesh modified GTR modified 64 minus 22 in the DGA mixture with the adjusted gradation. This BBR test method has been used, however, it is not among the more common tests such as SCB or semicircular bend test, the iFit, or the ideal CT. This data was readily available, and we didn't want to indicate a preference to any specific test. You can see that all the materials were in the pass zone at the 16 degrees C test temperature on the BBR. So, but the 22 degree test temperature, the 15% GTR was outside. It was in the fail area. That could be because, again, maybe there needs to be a little more adjustment on the mix to make room for the rubber in the asphalt mix. This slide shows a mixture testing on the 20 mesh, 30 mesh, and 80 mesh rubber that we mentioned earlier, as well as the hybrid and the SBS modified 76-22. In this case, you can see again that pretty much they all passed at -16, and they were in the somewhere in the risk area at the -22. This is an example of the hybrid. This is the example of the 76-22. And then, of course, you've got the 20 mesh. The main difference is the 20 mesh was in the fail area, and this was at the -22. And again, this could be because of the larger particle size, and like I mentioned earlier, just maybe a little more adjustment on the mix to make more room for the rubber might work for that. Now let's wrap things up with a summary. As a summary and recap of what we presented, modifying asphalt binders and mixtures with GTR is a commonly accepted practice for production of asphalt pavements. GTR is the second highest consumer of recycled tire rubber, with uses in several applications to include asphalt binder and asphalt mixture modification for asphalt pavement construction. GTR from old tires consumes about 16.5%, approximately 180,000 tons, or 11 million scrap tires of the United States, total United States GTR market. GTR modification of asphalt binders and mixtures can provide improved performance pavements that aid in reduction of waste tire disposed of in landfills and elsewhere. Post-consumer GTR polymer currently ranks second among the most common asphalt polymer modifiers behind SBS polymers. This webinar and the companion technical part are intended to provide a review and update of available GTR modified asphalt technologies in production of asphalt pavements. The objective is to provide knowledge for resource responsible use of asphalt rubber, rubber modified binder, hybrid GTR, and dry added GTR to ensure engineering performance in asphalt pavements. This information is limited to discussion of GTR from whole scrap tires through size reduction and grinding to a particle size range defined by the industry as GTR or ground tire rubber. Presented was information related to the design of dense graded asphalt, stone matrix asphalt, and open graded friction courses mixtures using asphalt rubber, rubber modified binder, hybrid GTR, and dry added GTR. At this time, I would thank you for your attention, and we will take questions and encourage discussion. Thank you.